Hey guys, and welcome back to Miss Danielson Math, where we're looking at functions today. Hopefully from this cover page you can see that we've got a function machine where we take values from the domain and put them into the function, and then values come out of the function to form the set of values in the range. Let's get started to see what that means, starting with the what is what. A function is like an equation or a formula with a given name. So for example, you might see function f or f of x, or function g or g of x. Really, we can use any letter we like to name a function, and we put input values, such as x or some number, into the function to find the output values. A function is simply a defined set of operations to be performed on a given input value. Functions can only have one possible output value for each input value, which may seem like common sense. When you perform a set of operations, you'll only get one answer. However, some of you might remember that when we square root values, we get a positive or negative answer. Well, that's not the case with functions. We only have a positive answer with these square roots and functions. The domains is a set of possible input values that we can put into the function. The range is the set of possible output values or resulting values from performing the operations in the function on the values we inputted into that function. Take a minute to copy those down before we carry on. Next, function notation. A function may be defined in one of two different ways. They could either say, for example, that function f takes the input value x and does this to it. So it does 2 times x plus 3. Now this is just an example of a function. Obviously different functions will perform different operations, but this function could have been defined in a slightly different way. This says that function f takes x and performs this operation on it. It multiplies x by 2 and adds 3 to it. I like this notation because you can clearly see here what the function's name is and the value that we substituted into that function. I'm starting us off with a function where the domain is pretty straightforward. Remember, the domain is the set of possible values that we could substitute into this function. Since the function just multiplies the input value by 2 and then adds 3 to it, we could do that to any value. So function f may have any possible input value. To define that using set notation, I could say that the domain of function f could include any x value where x is simply a real number. For example, I could substitute x equals 1 into function f. I say that f of 1 is the same thing as 2 times 1 plus 3. 2 times 1 is obviously 2, so this is 2 plus 3, which is 5. So my input value was 1 and my output value is 5. But I can input any value I like into this function. I can input whole numbers or decimal numbers, positive numbers or negative number. In this function, I can put any value in. So if I substitute negative 0.5 into function f, I call that f of negative 0.5. And that would simply be negative 0.5 multiplied by 2 and add 3. Obviously, 2 times negative 0.5 is negative 1, so negative 1 plus 3, which is 2. When I input negative 0.5 into function f, the output is 2. The range of output values are all the possible values that could come out of this function. Now, this is a fairly straightforward function where there's no restrictions to the domain, so we could put any value we like into this function, and there are no restrictions to the range either. Any value could come out of this function. So again, I could define the range as any possible y value, and I could use any letter I like here to define it, where that y value is simply a real number. Some other functions may need to exclude some values from their domains. In this example, function f is the square root of x minus 3. Now, something you need to know is whenever you see a square root in a function, you have to remember that we can never square root a negative value. The square root of a negative number will not result in a real output value. You can try that now on your calculator if you like. Hit pause and I'll wait. Try square rooting a negative number. your calculator gave you an error, didn't it? That's because those numbers are not real numbers. So in this case, since x minus 3 must be a positive number, we could say that the domain of all possible input values must be values defined by x, where x minus 3 is greater than or equal to 0. That means that x must be greater than or equal to 3. And x, of course, must be a real number. For example, I can input 4 into function f because 4 is a number greater than or equal to 3. If I substitute 4 into function f, I'd call that f of 4. That should actually be a 4 in there. And that would be the square root of 4 minus 3. So the square root of 4 minus 3, that is 1. So the square root of 1 is 1. So when my input is 4, my output is 1. However, I cannot input a value like 2 into function f because 2 is smaller than 3. If I input 2 into function f, I'll call that f of 2, and once again, this should be a 2 here. That would be the square root of 2 minus 3. 2 minus 3 is negative 1, and if you try square rooting negative 1 on your calculator, you'll get an error because that's not a real number. That's what we call an imaginary number. So since 2 only gives us imaginary output values, 2 must be excluded from the domain. As for the range, the output values will always be positive numbers. Since functions can only have one output value for any input value, we can't say that f of x is going to give us the positive or negative square root of x minus 3. We're only going to include the positive square root values. So here when I did the square root of 1, I didn't include positive and negative 1, only the positive answer. So I know that my range of values should always be positive, but there may be some more restrictions. To gain a better understanding about range restrictions for the function, we need to explore the domain restrictions for the inverse function. But that's a lesson for another video, so definitely look out for my video on functions and inverse functions. But for now, let's move on to some other types of functions. There are other rules which exclude some values from the function's domain. For example, in function g here, this function involves a fraction or a division, and you need to know that you could never divide by 0. That means that the denominator of this fraction, so x plus 2, cannot be equal to 0. It can be positive and it can be negative, but we can't divide by 0. So here I've defined my domain as being any possible value for x, where x plus 2 is not equal to 0. And of course, x is a real number. Simplifying this definition, that would mean that x could have any value except for negative 2. Because of course, if x was negative 2 plus 2 would be equal to 0. So x could have any value except for negative 2, and of course, x must be a real number. For example, I could substitute x equals negative 3 into function g. That's not a problem. That would give me a negative denominator, but it won't be a 0 denominator. So I could say that if x is equal to negative 3, g of negative 3 would simply be 5 plus 2 times negative 3 over negative 3 plus 2. Simplifying that, that's 5 plus negative 6, so 5 minus 6, over negative 3 plus 2, that's negative 1. 5 minus 6 is negative 1, so negative 1 over negative 1 is 1. When my input is negative 3, the output from my function g is 1. I can't put negative 2 into this function though. Let's see what happens when I do. If I put negative 2 into function g, so g of negative 2, I end up with 5 plus 2 times negative 2 in the numerator. Now that shouldn't be the problem. 5 plus 2 times negative 2 would simply be 5 minus 4. But in the denominator, I have 0. So regardless of what I got in the numerator, I can't divide it by 0. I've got 1 divided by 0, which if you try in the calculator, you'll see it's a math error, because that's actually infinity. And infinity is not a real number. Again, as my output is not a real number, I have to exclude negative 2 from the domain of input values. Looking at the range of output values, again, to understand more fully what values could come out of this function, you need to understand what the domain restrictions are for the inverse function. And as we haven't looked at inverse functions yet, we're only going to focus on the domains for now. If you haven't already, let's just make really clear those two rules for function domain restrictions. We can't divide by 0, so anytime your function involves a fraction, make sure that the denominator of that fraction is never 0. And we can't square root a negative value. So again, if your function involves a square root, make sure that the expression under that square root sign is never negative. So far, we've only been looking at inputting values into a function. We could just as easily be asked to find the possible input value that gave you the output value. So for example, 4, function h takes the input value, subtracts 3 from it, and then multiplies that answer by 5. If we're told that function h has an output of 45 when the input is a, let's work out what that input is. In order to do this, you need to simply remember that function h performs this to its input values. So when I say that h of a is equal to 45, that means that a minus 3 multiplied by 5 is equal to 45. Now I've just got an equation that needs rearranging to solve. I want to find out what a is, so let's get a on its own. I'll take this 5 to the other side. Here it's multiplying, so there I'll divide. 45 divided by 5 is 9. Now to get a completely on its own, let's take the negative 3 to the other side. The opposite of subtracting 3 is adding 3, so a is equal to 9 plus 3, which is 12. So when a is 12, h of a will give me 45. And of course, I can check that that's true by substituting 12 into this function. 12 minus 3 would be 9, and 5 times 9 does give me 45. Let's get on to some practice now. Complete these tables to find the missing input or output values. So if I give you the input value, put that input value into the function and calculate the output value. If I give you the output value, set the function equal to that output value and rearrange to find out what the input must have been. Take care with questions 3 and 4. There may be some restricted values there, either impossible input values or impossible output values. Now go ahead and hit pause, give that a try for yourself, make sure you show your algebraic working, and hit play when you're ready to take it up. I hope you had a chance to hit pause, because here come your answers. For question 1, when my input is 0, f of 0 would simply be 5 minus 3 times 0. 3 times 0 is 0, so 5 minus 0 is 5. F of negative 2, 5 minus 3 times negative 2. Negative 3 times negative 2, watch out, double negative there, is positive 6. 5 plus 6 is 11, so my output is 11. Next, I gave you the output value, so set the function equal to negative 1. Rearranging that to get x on its own, subtract the 5, divide by the negative 3, x would be 2. So my input value is 2 when my output value is negative 1. You could check that by substituting 2 into that function. You'll see you get an output value of negative 1. Next, f of 4. 5 minus 3 times 4 is 5 minus 12, which is negative 7. So when the input's 4, the output is negative 7. Function g, g of 3 would be 3 times 2 times 3 plus 1. 2 times 3 is 6. 6 plus 1 is 7. 3 times 7, 21. So my output is 21 when my input is 3. Next, if my output is negative 3, I'll set my function equal to negative 3. Rearrange that to get x on its own. I first multiplied the 3 through. I could have also started by dividing by 3. Then I got my 3 to the other side. Then I divided by 6. So when my output is negative 3, my input must have been negative 1. And I can try substituting negative 1 back into the function. 3 times 2 times negative 1 plus 1 should give me an output of negative 3. Next, when the input is 2, g of 2 will be 3 times 2 times 2 plus 1. That's 3 times 4 plus 1. That's 3 times 5. That's 15. So when my input's 2, my output is 15. Finally, when my output is 0, let's set that function equal to 0. Let's rearrange it. And x is equal to negative 0.5. Again, we can check by substituting negative 0.5 into that function, and you'll see that the output becomes 0. Function 3 with this star here, let's watch out. Where was this a difficult or trick question? Can I substitute negative 1 into this function? I don't see any fractions or square roots, so I would think that I can. H of negative 1 would simply be 5 times negative 1 squared. Negative 1 squared is negative 1 times negative 1. A negative times a negative is a positive, so that's 5 times 1, which is, of course, 5. So when my input's negative 1, no problem, my output's 5. Can I substitute 2 into this function? H of 2 would simply be 5 times 2 squared, which is 5 times 4, which is 20. No problem there. When the input's 2, the output is 20. Next, how would I get an output of negative 20? Set the function equal to negative 20, and let's see. Let's rearrange this. So I'll move the 5 to the other side. Opposite of multiplying by 5, we'll divide by 5. Negative 20 divided by 5 is negative 4. To get the x on its own, the opposite of squaring is square rooting. So x is equal to the square root of negative 4. If you try that on your calculator, you'll see that you get an error because this is not a real number. You can't square root a negative value. So there's no way I inputted a real number into function h and got an answer of negative 20. Therefore, we must exclude negative 20 from the range of h, because you could never square a number and then multiply it by 5 and expect your answer to be negative. All square numbers are positive. Next, 0.1. h of 0.1 is simply 5 times 0.1 squared. 0.1 squared, 1/10 times 1/10. That's 1/100th. So that's 5 times 1/100th, which is 5/100ths. No problem there. When the input's 0.1, the output is 0.05. Question 4 has also got a star there. I wonder why that might be. Can I input 3 into this function? K of 3 would simply be 12 over 3 minus 1. 3 minus 1 is 2, so that's 12 divided by 2, which is 6. No problem there. When the input's 3, the output's 6. Can I get an output of negative 3 from this function? Let's try setting the function equal to negative 3. Rearranging that to get x, I'm going to need to take the denominator of this fraction to the other side and multiply by it. And then try and get x on its own. So start by dividing by the negative 3 and moving the negative 1, so adding the 1. And my input must have been negative 3. So if my output's negative 3, my input must have been negative 3. I can try substituting negative 3 into function k, and I'll see that I get an output of also negative 3. Can I input 5 into function k? K of 5 would simply be 12 over 5 minus 1, which is 12 over 4, which is 3. Yep, no problem there. If the input's 5, the output is 3. Can I possibly get an output of 0 from this function? Let's set up that equation. When is the function equal to 0? Again, let's rearrange that function to find out what x is. Take the denominator across to the other side and multiply. If I multiply that out, however, I get 0. How can 12 possibly be equal to 0? That's not possible. I can't possibly get an output value of 0 from this function. Therefore, 0 must be excluded from the range of output values for function k. Here's a bonus question. See if you can work this out for yourself. Although this is quite a bit more challenging than the previous questions, it is a typical exam question. I've got function f and function g defined here. Find the value of x, given that f of x is equal to g of x. So set these functions equal to each other and work out the input value that gets the same output value out of both functions. Go ahead and hit pause and give that a go on your own, and we'll take it up in just a minute. I know it's challenging, but I hope you hit pause so you can try that on your own. Here come the answers. If f of x is equal to g of x, 1 plus x must be equal to 12 over x. Rearranging this to find out what x is, I need to get my x's to the same side of the equation. So I'll start by taking the denominator of this fraction over to the other side and multiplying by it. So I've got x times 1 plus x. Multiplying that through, that gives me x plus x squared. And uh-oh, there is an x squared in this equation. That makes this a quadratic. And we can't solve a quadratic unless it's equal to 0. If you're not familiar with quadratics, make sure you check out my quadratics video. I'll link them down in the description box for you below. Now this quadratic ends up being fairly simple because I know we can factorize it. The alternative is to use the formula, but I always recommend factorizing when you can. Can you think of two numbers that multiply to make negative 12, but add to make positive 1? I can. Positive 4 and negative 3. Well, that's embarrassing. This should be 0 here, because that's the only way I could solve this quadratic, is if this is equal to 0. So that's just a typo. But if something multiplied by something is equal to 0, then either this is 0 or that's 0. So either x minus 3 is equal to 0, in which case x is equal to 0 plus 3, so x must be equal to 3. Or the x plus 4 is equal to 0, in which case x is equal to 0 minus 4, which is negative 4. So there are my two possible values for x, which could substitute into function f and function g to make them equal to each other. Now I can always check this, and I highly recommend that you do. Is f of 3 the same thing as g of 3? If I substitute 3 into function f, I get 1 plus 3. If I substitute 3 into function g, I get 12 divided by 3. 1 plus 3 is 4. 12 divided by 3 is also 4. So yeah, when x is equal to 3, f of x is equal to g of x. But also, when x is equal to negative 4, f of negative 4 would be 1 plus minus 4. Now plus minus, that means subtract. And 1 minus 4 is negative 3. G of negative 4 will be 12 divided by negative 4. And 12 divided by negative 4 is also negative 3. So that works as well. F of negative 4 is equal to G of negative 4. And that brings us to the end of our lesson. I hope you found this lesson helpful and interesting, and I hope you check out some of these other videos as they help you along with your studies. I apologize for the typos we made today. It happens, right? We all make mistakes. Till next time, keep practicing, and I'll see you soon.